Hi again. This is the second of 3 lectures presenting a stepwise method for sizing the battery for an electric vehicle. This time we will analyze the power that's required from the battery, both during discharge and regenerative charging. In this diagram we see the energy consumption when driving a long distance according to the NEDC cycle. If we zoom in on different parts of the cycle, we see that the energy curve is made up of the same energy consumption curve over and over. And since the power is determined by the driving cycle, the same power variations will occur over and over again from a battery state that is fully charged and all the way to an empty state. So there are no good reasons to assume that demanding driving situations can only happen at certain segments of the 300-kilometer driving range. So we have to assume that every power level which the battery is required to provide can occur at any state of charge. In other words, the power demand is independent of state of charge. We may still select to allow the battery to provide less power when it's close to fully discharged, but it is not because demanding traffic situations cannot occur at the end of a driving cycle, but rather because it's more valuable for the driver to allow the longer range than to shorten the range just because the power requirements cannot be met at low state of charge. When we calculate the required battery power, we will once again use the powertrain model. The power from the battery can also be calculated with QSS, but since it's only necessary to analyze a few operating points, we will instead show how they can be analyzed one by one. We only need to calculate the power required at the battery terminals, since that's what's used in our description of the operating region of the battery. In our models we have assumed the transmission efficiency to be 100%, and we have a model defining the efficiency of the electric drive system as function of the torque and shaft speed of the electric machines. We can then calculate the battery power as the traction power divided by the electric drive efficiency. In this diagram we can find the efficiency of the electric drive system. To find the efficiency for a certain requirement, we first have to find the operating point for the corresponding driving situation, like we did in a previous lecture. So when we know the torque and the speed of the electric machine, we can find the operating point. By interpolating between the contours, we can get an estimate of the efficiency in that operating point. In this case, it's 91%. These are the required operating points for the vehicle in our example. We only need to meet the most demanding of the positive and the negative battery power requirements respectively. But since the efficiency varies with operating point, we cannot be sure it's the requirement with the highest traction power that will lead to the highest battery power, even though this is actually often the case. So it makes sense to at least analyze the requirements with the traction power close to the one with the highest traction power. For the operating points with a high traction power, we calculate the battery power as the traction power divided by the total efficiency of the electric drive system. This is the operating point with highest traction power. The drive system efficiency is 93%, leading to a battery power of 102 kilowatt. This operating point has a traction power of 84 kilowatt and efficiency 92%. Leading to 91 kilowatt battery power. And here we have 75 kilowatt traction power and 90% efficiency, leading to 83 kilowatt. Since the efficiency is often lower at peak torque, we also check this operating point. Here 69 kilowatt power and 87% efficiency leads to 80 kilowatt battery power. So the highest required battery discharge power is 102 kilowatt. And this is the required operating point which puts the highest discharge power demand on the battery. We mustn't forget to check the other side, which operating point leads to the highest charging power. Since the power changes direction, so to speak, the battery power is now the negative traction power multiplied by the total drive system efficiency in generator mode. Regeneration in 100 km per hour have a traction power of minus 22 kilowatt, and the efficiency is only 80% at this low power, leading to minus 18 kilowatt battery power. Regeneration at 50 km per hour is minus 22 kilowatt at an efficiency of 90%, leading to minus 20 kilowatt battery power. The latter has greater absolute value, so we will use this one for battery sizing. Now we will use both the discharge requirements and the charge requirements to determine the maximum range of battery power used by this vehicle. This is the vertical axis of the battery operating region diagram. The highest discharge power is the upper power limit, and the highest charge power is the lower limit. So again, now we know the required power range for the battery for this vehicle. It is between minus 20 up to plus 102 kilowatt. Now we have determined the power range within which the battery should be able to operate. Let's stop here for a moment. Please try the exercise following this presentation before we do the last part.